So welcome to the final plenary session of TeVPA 2017. It's a pleasure for me to introduce our first speaker, Samaya Nissanke from Radboud University, Nijmegen. All right, so she's going to tell us about gravitational waves and follow-up and figuring out what these things are. Okay, take it away.
So good morning, everyone. Thank you for coming to the last session. And before I start, I'd like to thank the organizers for asking me to talk about gravitational wave astrophysics with a focus on electromagnetic follow-up, particularly in this very exciting time where we've seen this tremendous convergence of several diverse fields, gravitational wave physics, transient astronomy, computational astrophysics, and more recently, dark matter and binary evolution all coming together in order to actually make this push forward in understanding strong field gravity astrophysics. And of course, we have now entered this new era of observational gravitational wave astronomy. And so last year, we announced the direct detection of black holes, gravitational waves, and binary black holes that merge. So with the two LIGO detectors, we observed 3 binary black hole mergers and 1 candidate that occurred within a fraction of a second at a redshift of approximately 0.1 for the first 2 events and 0.18 for the final event, the third event that was announced a couple of months ago. And what I'd like to stress is that these are the most luminous events that we've observed in the universe. For the first detection, 3 solar masses of energy were released during the merger, and the first, second, and third events produced black holes with masses 62, 21, and 49 solar masses respectively. So not only have we actually detected black holes, but we've also uncovered a surprising diversity in the black hole masses and are probing this new parameter space, which is complementary to the black hole masses that were previously inferred from dynamical mass measurements by X-ray studies. However, what remains unknown is what's behind this diversity. Okay, so we heard earlier this week are these primordial black holes that were generated from fluctuations in the early universe, or indeed do they form from the more conventional channel of the death of pairs of massive stars? And arguably, the next big discovery that we're awaiting is actually to measure a compact object merger in terms of the gravitational wave and electromagnetic observation, where at least one of the compact objects is a neutron star and has associated matter to it. And so within the frequency band of these advanced gravitational waves, we aim to track thousands of tens of thousands of cycles of the in-spiral as they're losing energy and angular momentum due to gravitational waves in the final minute. And during the complicated merger, we expect there to be some unbound material that occurs tens of milliseconds post the merger, and it's this that's responsible for these electromagnetic counterparts that occur at different frequencies and different time scales. And of course, the big game changer today is that we can actually detect both the gravitational wave and electromagnetic, as well as high energy neutrino radiation, with this whole slew of time domain telescopes that have come online, essentially monitoring the dynamical and variable skies. So from gravitational waves, we'll learn about fundamental source parameters of these systems, such as the masses, the spins, the neutron star equation of state. And from the electromagnetic radiation, we'll learn about orthogonal and complementary information, such as the environment sources, the sources environments, and the energetics. And of course, it's necessary to actually combine these 2 complementary probes in order to actually put these compact object mergers in their full astrophysical context. So in the next, for the rest of my talk, I'm going to briefly describe how we actually retrieve black hole parameters from gravitational waves. Secondly, I want to briefly discuss actually what happened in terms of the electromagnetic follow-up for these binary black hole mergers and the lessons learned. And finally, I'd like to end with my own perspective on how to actually connect gravitational waves to astrophysics with EM counterparts. So let's go back to the first detection. These tremendous plots, I think, really encapsulate gravitational waves. So shown in the top panel is the raw gravitational wave strain, which has been bandpassed and whitened, that was seen as the Livingston detector, and then 7 milliseconds later seen at Hanford, Washington, 3,000 kilometers away. And in the bottom panel, you can see the time frequency spectrogram, and very clearly marked is the signal shown in yellow above the detector noise shown in blue. And what I'd like to spend a couple of minutes describing is how from these simple shapes we can actually infer fundamental properties of the black holes. So for this, I'd like you to note the morphology, that there are about 10 cycles in band, and secondly, that we have this characteristic frequency chirp indicating an ever-increasing frequency in a frequency map. So already in these plots is encoded a wealth of information that impacts the astrophysics as well as allows us to perform null tests of GR. So gravitational waves, they're perturbations in the curvature of space-time. They travel at the speed of light. They're sourced by accelerating quadrupole matter sources. And the dominant and lowest order radiation is given by the Newtonian quadrupole formula, where Ij here is the quadrupole mass moment. And it's important to note that the measurable, our observable, is this gravitational wave dimensionless strain, which is a 1 over distance to the source dependence. And so they're coherent, they're weakly interacting and allowing us to actually probe the dynamic bulk properties of the matter. And there are two polarizations, H plus and H cross, which essentially act as transverse tidal fields as a gravitational wave passes through. And this is precisely how these gravitational wave interferometers are measuring gravitational waves, by measuring this linear combination of the two polarizations as they tidally stretch and squeeze the arm lengths. And so the fractional change in arm length of these interferometers can be seen to be proportional to this gravitational wave strain. So for astrophysical strains that we've seen of 10 to the minus 21, for kilometer length interferometers, we're talking about delta L's of 10 to the minus 18 meters, a thousandth the nucleus of a hydrogen atom, and therein lies really, I think, I guess I'm not American, but the awesomeness of gravitational wave interferometers. And so from 30 hertz to a couple of kilohertz, in spiraling neutron star binaries and then merging binary black holes are really the prime sources or the strongest and most numerous sources that we expect. And we can understand essentially how this frequency increases and evolves by simply considering a Newtonian description of a binary system. So if by using essentially the Newtonian orbital energy as well as this Newtonian quadrupole formula that I showed previously, invoking energy balance, and within a couple of steps you can get an expression for the frequency chirp. So essentially by measuring F and F dot, you can obtain immediately an estimate for the chirp mass. This is a combination of the two masses of the systems, which was 30 solar masses, already implying that the total mass of the system was above 70 solar masses. And from the maximum frequency, we could already tell that the orbital separation just before they merged was 350 kilometers. And I remind you that the Schwarzschild radius for a 70 solar mass black hole system is 210 kilometers. So immediately, we were able to know, if this was real, that this was a binary black hole merger. Now, for the second event, it was barely visible in the time frequency spectrograms. In order to extract information, you need to actually have a very accurate model of what you, of the predicted gravitational wave strain. We call these waveforms, and these comprise these three phases, the in-spiral, the merge, and the ring down, which basically correspond to different parts of the binary black hole evolution. And as I've mentioned already, there are a few things I'd like to point out. The in-spiral is essentially driven by this quantity, the chirp mass, which appears in the Newtonian, at Newtonian order in the amplitude and the phase of the source. And in the ring down, which basically describes the final settling of the remnant black hole, encodes essentially the remnant mass and spin. Okay, and so I'd just like to stress that this so-called in-spiral describes, is given by a set of well-defined orbits, essentially which are adiabatically evolving due to the gravitational wave back reaction. This merger is essentially the most stringent test we have in general relativity when these two bodies essentially become one. We're talking mathematically of two black hole horizons becoming one. And the ring down, as I mentioned, basically enforces the no-hair theorem. Yes, so it's described by a damped sinusoid, and the damping frequency and time essentially give you the mass and the spin of the final black hole. It ensures that we actually, that this final remnant is the Kerr solution. And so by measuring at least more than one mode of this actual ring down, we can actually do consistency tests of the no-hair theorem. We haven't been able to so far because we haven't accumulated enough signal-to-noise ratio for the first three detections in the ring down. The second thing I'd like to stress is that the in-spiral and the ring down can be modeled extremely accurately using perturbative techniques in general relativity, such as the post-Newtonian approximation, where v here is the characteristic orbital velocity, and quantities like the reduced mass happen at higher post-Newtonian order in the gravitational wave phase, as well as spin effects happen at even higher order and are responsible for essentially the beating and the modulation that will be seen in the actual waveform. Okay, so really there's an incredible amount of information that's encoded in this chirp. And so what I'm showing here is just an example of the equations of motion for one of these binaries. And for the students in the room, I just want to state this was my first project in my PhD, was actually computing this term. And every numerical coefficient here was actually critical and is actually a prediction of general relativity. I'm just flashing it up just to show the detailed, the detailed and accurate description that we have just from analytical relativity. Now, of course, just as we come to merger, these black holes are traveling at about half the speed of light, so we actually have to directly solve Einstein's field equations using numerical relativity. And of course, there was tremendous success there. And so in the last decade, there's been a lot of effort in building these analytically inspired, coherently sort of full in-spiral merger ring-down waveforms. And with these in hand, which are calibrated to numerical relativity, you can then actually cross-correlate a template bank of these waveforms with your detector output. Typically, it's about 10 to the 5. And you can explicitly map out your posterior probability density functions of some vector set of parameters using stochastic random sampling techniques and actually extract information, key information such as the redshifted masses, the redshifted spins that appear in the gravitational wave phase, and geometric properties such as the inclination angle, the source position, and the luminosity distance that appear in the amplitude of the source. And so what I'm showing here are the 2D PDFs for the first detection. It's shown in blue and in orange for the second detection. And these are the 90 and 50% confidence regions for mass 2, mass 1, the final spin, the final mass, the effective spin. This is a mass-weighted combination of the spin components that are perpendicular to the orbital plane, the mass ratio, as well as the 1D PDF of the distance. And what I want you to take away is the large degeneracies that you can see between certain combinations of these parameters. So this means that the relative errors are tens of percent. The second thing I'd like you to take away is that we have very poor constraints on the spin of the progenitors. This essentially where we think that the spin of the progenitors will really give us a telltale sign of where these systems are actually being formed. And the third thing is that we have quite poor constraints on the distance because of this inclination angle distance degeneracy that appears in the waveform. And all of this is due to the fact that the errors depend very much on what epoch of the waveform is, the detector sensitivity is sensitive to different epochs of the waveform depending on the total mass of the system. So in the first, second, and third detections, we were able to track 10, 55, and 15 cycles. Yes, so in order to actually say whether you're going to be more sensitive to the progenitors or else the remnant mergers, this really depends on how many cycles. And this has an important consequence when we're talking about neutron star binary mergers, where we'll be tracking thousands to tens of thousands of cycles. Okay, so we really have exquisite measurements on the in-spiral. So coming up to the follow-up, so how well could we actually localize these sources? Well, these detectors have very broad antenna functions, they're quadrupolar, and so you need to essentially have 2 or 3 detectors to actually constrain the source on the sky. So with only the 2 LIGO interferometers shown here are the sky errors for the actual first 3 detections. You can see there are huge swaths of the sky, and I'd really like to stress that using the distance information, in these gravitational wave volumes, we're talking about 10 to the 5 to 10 to the 7 galaxies. So you really can't say very much at all about the actual host galaxy of these sources, okay? And for the first event, despite this huge sort of 590 square degrees, 24 observatories out of 70 partner observatories actually followed up this sky area, which spanned 19 orders of magnitude in frequency space. The observational epoch shown in red are for the radio, the optical IR are in green, X-ray blue, and gamma ray was all sky down to this sensitivity. And of course, there was also high-energy neutrino searches with IceCube and Antares. And so it was really very, very remarkable. However, there were a few things that I think it's important to state that we learned from the first observation. Firstly, that the required depth that a lot of these telescopes took observations of was not necessarily deep enough, and this is because the nature of the source or the distance information was not shared with our EM partners until about 3 weeks after the first detection. And the first alert was actually sent 3 days after the first detection. Of course, this was because it came as somewhat of a surprise, as well as the fact that stellar mass binary black holes were thought not to actually have electromagnetic counterparts. However, I'd like to stress that today, the last event that happened in January was actually sent out within 7 hours of the actual detection with information about distance and the source nature. So this is actually going to improve and dramatically, we're hoping to get this down to 30 minutes. The second is obvious. The second is that in these huge swaths of the sky, there are many, many other events that are actually happening, transient and variable. So for the first event, there were a whole host of events happening in the optical. And so this is a sort of Where's Wally cartoon of the actual challenge, and Wally or Charlie is here. And so our EM counterpart that might not necessarily be in the center of the field of view, but I'd like to stress that this is sort of really one of the big challenges that we have to face. And in order to actually deal with all these other astrophysical false positive transients, knowing the gravitational wave distance and the redshift was critical. In the interest of time, I will just mention that there was an interesting subthreshold Fermi GBM EM counterpart that was reported from archival images 0.4 seconds after the event, lasting 1 second. And as soon as the paper came up, it was very, very, I guess, heartwarming to see a lot of very creative and exciting papers, theory papers being proposed to actually explain how could you actually produce such a high energy emission, ranging from collapse-alike to a binary black hole being embedded in the AGN disk, as well as an ultra-fast mini-disk from a third body. Some of the authors are actually in the room, but I would like to stress that no candidate was actually reported by the integral satellite that was also looking at the same region. So in the last 5 minutes, I'd like to sort of look forward. Of course, the challenge that we face today now with all the measurements I've discussed of the 3 detections is we still have to answer how, where, and when do these binary black holes form. If they are forming from pairs of massive stars, do they happen in isolation due to classic field binary evolution or due to dynamical formation in dense environments? This is still unanswered. What we have been able to say is in order to form the very heavy stellar mass black holes, you need to invoke weak stellar massive winds, as well as have low metallicity environments. But it's clear that in order to make progress, I think we need to do joint analysis of the mass distributions, the spin distributions, as well as the host galaxy distributions. But this, of course, brings us on to why we want to have an electromagnetic counterpart in order to actually be able to pinpoint the host galaxy. And so broadly speaking, from neutron star binary mergers, we expect there to be 2 types of matter outflows, those coming from tidal tails and disk winds, and those coming from ultra-relativistic jets. And these outflows result in a plethora of electromagnetic counterparts that have been proposed. So shown here are the phases as a function of time in the lifetime of a neutron star binary merger. And the observables are shown in this panel, as well as the physical processes here, but I'll just mention that there have been proposed radio or X-ray precursors due to resonance shattering flares. Short GRBs, of course, are thought to be due to the progenitors of neutron star binary mergers. And there's been a huge amount of interest in these isotropic OIR counterparts dubbed kilonova and macronova, which are due to some unbound ejector, which is very neutron-rich, which undergoes rapid neutron capture nucleosynthesis, acting as a thermal source, as well as synchrotron blast waves coming from this ejector as it hits into the ISM. So there's a whole plethora, and of course, we would love to have all of the electromagnetic information that we can have in order to really piece together the physics of what's driving the merger. And so, of course, the next step is actually to combine and interpret both the gravitational wave gravitational wave measurements with our electromagnetic signatures, particularly things like the redshift, the source position, as well as information as the ejector mass. And to do this for strong signals, to characterize these, to really do a full characterization, as well as to do this for populations in order to actually say something about compact object mergers, their demographics, the ecology, and the census. And so for me, this really is sort of the next step that we have to take when we talk about doing gravitational wave or multi-messenger astronomy, is to understand what are the degeneracies between these two parameters and how we're going to actually combine these data sets with their different instrument systematics. And so just to end, in the next years, we will be expanding our worldwide network of gravitational wave detectors. Currently, we're actually in the second science run, which began at the end of last November and will end at this month, where we have 81 days of coincident data as of the 23rd of June. But of course, the very exciting news is that Virgo actually joined this science run. This is the interferometer that I'm actually associated with, located in Pisa, on August the 1st. And this has immediate consequences for electromagnetic follow-up. Really, particularly because we can actually start to triangulate the sky localization of these sources. So even with Virgo not being at perhaps at half the sensitivity of the LIGO detectors, you can already see for the first event from 600 square degrees, the error shrinks to 10 to 20 square degrees. This is, of course, a simulation. And with the Japanese detector and LIGO India, where the aim is to have these operational at design sensitivity in the early 2020s, you can see that this actually reduces even more by several factors. So we're talking about square degrees, okay? So really, this is where we're going in some sense with the EM follow-up. And so one of the strategies that is now actually being taken by many telescopes is assuming that the compact object merger happens within a galaxy, the binary black hole or the neutron star binary merger. We can cross-correlate not just the sky position, but also using this distance information, which was something I suggested several years ago. You can cross-correlate this with galaxy catalogs and actually start either to use this in order to actually target known galaxies for small field of view telescopes such as SWIFT. This is actually taking place. So in a work led by Neil Gehrels, where we considered essentially how many of the brightest galaxies that produce 50% of the light would be within these gravitational wave volumes with different sky areas and different distances. It was about on the order of about 25 galaxies. Okay, so this is one way to actually go ahead and target. The second way is actually just to use the spatial coincidence of these galaxies with these gravitational wave events to actually reduce the false positive number by tens to 100. And so I'm going to end now just to say that we have, of course, just begun probing the high frequency part of the gravitational wave spectrum that spans decades of frequency space, but of course there are attempts already happening to actually detect gravitational wave measurements in other parts of the spectrum. And of course, this will allow us really to probe the astrophysics of a whole plethora of different sources. And so I'll end by saying the immediate future is extremely loud and bright. In the coming years, we can expect the gravitational wave detector sensitivity as well as the networks to increase, and we have to be prepared for the first gravitational wave EM detections, as well as the fact that we will have potentially tens of binary black hole mergers per year coming out. It will be challenging to find the EM counterpart, but they will provide, I think, the methods and the tools are already there for this to happen, as well as the facilities. They will provide key complementary information about the fundamental source parameters, and it's a key step that we have to actually do this joint analysis of all the different parameters that we will actually learn about these systems. And so, of course, beyond this era, we're witnessing the entire opening up of the gravitational wave spectrum, and yes, I hope you'll agree with me that really this is going to be a very, very fun and exciting decade. Thank you.
All right. Thank you, Samaya. We have time for a couple of questions. And again, the lights are blinding us a little. We're blinded by the light. Okay.
Hi. So what's the current status of searching for the kilonova events? Like I know Black Gem is designed to do that. Can you comment on that more?
Yes,
yeah.
Thank you very much for mentioning Black Gem. So actually there have been a few tentative observations of kilonova already that have been seen coincident with short gamma ray bursts, which I didn't mention. And so, but however, we don't actually have the sort of smoking gun confirmation that these are kilonovas, but indeed, there are many efforts in terms of wide field telescopes, such as the Zwicky Transient Facility, as well as Black Gem, a telescope that I'm associated with in the Netherlands that is really prime to actually go after these kilonova measurements. One of the key uncertainties actually at the moment is what the opacities of these systems are. And so, because you're building up all these rare earth elements, the opacities are thought to be at least 100 times greater than a standard supernova. So I think this is one of the key uncertainties from the theoretical modeling, but in terms of the observational capabilities, there's a whole slew, as well as the dark energy camera, pan-stars, etc., that are really prime, hyper-supreme cam on Subaru, they're all primed to go after this OIR counterpart. Yes, so that's a great question. I think, in terms of actually having the confirmation will obviously be to associate it to a gravitational wave event, as well as potentially to a short GRB, and having spectroscopic confirmation, I think, will be key as well. Really being able to say something about what is it, what are the constituents of the ejector. But I do also think things like the radio counterparts are looking also very, very positive in terms of potentially being the first counterparts that we will see.
So you talked in the beginning of the talk about testing the whole framework of general relativity. So is there a particular source that would be most interesting in this context? And also, for the electromagnetic counterpart, if one were to be found, does that substantially help in the ability to test the GR framework?
So yeah, thank you for that question. So in terms of testing GR, I think I think the most stringent test in some sense will come from looking at, for instance, the ring down as well as the merger of these binary black hole systems, yes? Because there we really are testing the strong field gravity regime. And so, but as well as, so I think, having a heavier system with higher signal to noise ratio, for instance, for the ring down will allow us, for instance, to really begin to, test things like the no-hair theorem, or at least do null tests of the no-hair theorem. With regards to how electromagnetic counterparts can help with fundamental physics, I personally think they will be able to help, for instance, in terms of things like we can actually test the propagation of the speed of light, etc., using gravitational wave and EM observations. But the second thing also that electromagnetic observations will help will be actually to constrain the fundamental source parameters of the system, and therefore to actually look at deviations from general relativity. But I think this is really a new field, and going beyond just doing, so far, what most groups have done is actually just perform null tests of general relativity, or begun to think about going beyond the standard model. But really now to actually have testable predictions is, I think, the next step in order to look at alternative theories of GR.